Guys, am I audible? I just hit record now, so let me know if you can't hear me. Good afternoon. Molweni. Dumelang. I hope you guys can hear me. So guys, like I said, it will come in exam, but it's of smaller magnitude in terms of marks and is part of the content. Yeah, so try to enjoy the section. Yeah, it's just a few things. If you open a textbook, where's my textbook? It's in my bag here. Just want to get it. So let me close the door as well. You notice there's like a few problems. Oh, it's 9 or 10. Just give me a moment. Yeah, obviously this is coming in the final, but like I said, nothing to focus on now. Let me just have a look. It's how many pages? Around 9 problems, I mean. And I will post some extra ones for people who's willing to, work a bit more and understand the concept of buckling, if need be. So it's not a lot, but there is one thing I will highlight drastically within this chapter, which you must absolutely know. Okay, let's move on. Chapter 15, page, if you want to follow, obviously, what's it, 2 to 1?
2 to 1.
Yeah, thank you. So guys, we've come a long way. It's the last lecture for MAE 200S. And again, we literally walked in that fashion of tension, compression, shearing, torsion, and bending. We've done all kinds of analysis, all the basic forms of analysis on them. We've combined some of them. Yeah, and then there's a last one called buckling, which is not a load, right? So I want to be aware what buckling is. Don't treat it as a family member within those pictures. I don't know. I just found this picture with buckling there, but before we actually begin, and obviously there's people who has watched the video too. Who has any idea what buckling perhaps is? Can someone please tell me? Just to initiate a small discussion here.
Buckling is probably when the how do you say, either the bending stress or the I think I would say bending stress exceeds the yield stress or the plastic limit of the beam or something like that.
No, that's not true. I can ask you another question. What's the difference between bending and buckling then? Just by observation.
Buckling is a deformation. Buckling is like a deformation of the beam.
Good start, yeah.
Oh,
and
buckling would be when it caves in on itself. Due to a direct load. I said buckling would be when your beam or object caves in on itself.
When you say direct load, you probably mean an axial load. I'm assuming that's what you mean,
An axial load is, yes, not
yeah.
A bending load, sorry.
Yes, right. So that's a bit better, right? So it's not like bending where you're looking at a transverse load, right? But we'll discuss that now. So just a Mickey Mouse observation before we actually decide to unpack what this is. Nothing heavy, students. So before, what's important of buckling, just like a formal definition of a strut. We all know what a strut is. The chapter is, of course, struts. And yeah, so strut is defined as a structural member subjected to compression in direction parallel to its axis. So we look at the question over there, it's essentially talking to what Mr. Kiefer has said. And that's basically a member which is being compressed, right? As we know what compression is. Obviously, we're familiar. Albeit that one must be aware, but the difference between the compression and another thing which we'll discuss is for longer pieces of it's called typically a column. It's a longer piece of a long strut, basically. Long strut tends to fail under, not fail under buckling, but it's a form of stability or instability, which one must check in the strut. Okay, and it just says the term strut is commonly used for compression members in roof trusses. Yep, the strut may be used in a vertical position or in the inclined position in the roof truss. Obviously, we're aware of that. I want to throw a picture there, but I thought, okay, it's kind of, we all can imagine that already. And obviously, we're aware of columns and things like that. Now, this is, I guess, the text is quite important. So obviously I'll read it to you, but like this is what really encompasses what all thing we're doing. And obviously I have a few numerical examples / experiments I wanna play around with and see what we can do. But anyway, so it says whenever a member design, it is necessary that it satisfies specific strength, deflection, and stability requirements. Obviously, we've looked at strength. That's talking stress. It can withstand a specific load. Deflection, we also had a look at deflection. Remember, you had deflection limitations. And now something called stability. And obviously, you guys are aware of stability. This is like something in the nav octane. And anyway, it says in the preceding chapters, we have discussed some methods used to determine a member's strength and deflection. Right? But we've always assumed that it was in a stable equilibrium. So I don't unpack too much of that, but you get the idea. Now, they say some members, however, may be subjected to compressive loadings, and if these members are long and slender, I mentioned that earlier on, I should have said long and slender, the loading may be large enough to cause the member to deflect laterally or sideways, right? That's talking to this. So it's long, not stubby, long and slender. It can displace, right? I'm going to call it displace for now, deflect laterally or sideways, right? Either X or the Y direction. And anyway, so they're saying to be specific, long slender members subjected to an axial force are called columns, and the lateral deflection that occurs is called buckling. So that member there, what is doing that is called buckling. You apply an axial load. What tends to happen is that the column or the long slender member, it buckles laterally, it moves sideways, right? Quite often buckling of a column can lead to sudden and dramatic failure of a structure or mechanism, and as a result, special attention must be given to the design of columns so that they can support the intended loadings without buckling. So what I'm making aware of, so if you were to design a column or what design people who design the columns in particular, one of the criteria they check for is obviously I don't fire under compression, and one of the second things, the second main thing is they check for that the column won't buckle. So it's one of those things which kind of I don't know what's the word I'm looking for. It's part of a column's design. Like for bolts, for instance, if you design a bolt, you have to design for the bearing stress, the tensile, and the shear. There are three conditions one must design for. The bolt can fail in three ways. So essentially, a column can fail in two particular ways, which is either under compression or buckling. So that's one of those things. Again, this is just from the previous lecture slides, and it says if the members long in comparison with cross-sectional areas determine slender, that's what we call slender, and we'll offer you to do buckling. Another word for buckling is also called crippling before the yield. So I just want to talk about that. What's important is that, let's say if you have 100 kilonewton you're applying to a particular member, right? Obviously in this buckling form, this long slender member, static slender, as we call it, as we say. And 100 kilonewtons over a specific area is let's say you apply it and the stress becomes for steel member, which is typically 355, we get a stress of 300 megapascals. We know that 300 megapascals is less than 355, therefore it won't fall the compression. However, buckling doesn't look at the yield or the allowable stress. It's something completely different. It solely looks at the load itself. So the column itself will have a buckling criteria or a buckling load. So if the buckling load for a particular column is, I said 100 before, was 50, and we apply 100, that means that column will buckle. So there's nothing to do with even the yield at all. So it's another phenomenon, that's not what I was giving, another phenomenon which arises from loading a column. It's also defined as an actual load. You should keep the static bend form, right? Obviously, we mean laterally displaced. Furthermore, let's say the calculation of the cross-sectional area of a compression was usually based on the buckling load and not on the yield, right? Or the maximum strength, is the factor of safety, as the case of the tie. So that's very interesting. Can I just say that again? The calculation of the cross-sectional area, excuse me, of a compression member is usually based on the buckling load and not on the yield. So I mentioned to you the two factors. I said we check if the elbow stress will be exceeded, and in the buckling, no, it's for buckling first. Buckling is key with columns. Obviously, it's a long slender column. And we obviously unpack that because there's different criteria you need to check. But anyway, so it's a very, very important thing, especially in column design. So one must be aware if you're designing. In fact, if you think about a connecting rod, Rima showed them a machine design textbook, if you can recall. And I'm just looking for, I'm looking at my other design textbook here. And I think the connecting rod, they actually use some analyses for the connecting rod, because that's a strut, if you think about it. And to ensure that the thing doesn't buckle, one needs to actually check for buckling, that the thing doesn't buckle with a given load. Obviously the fluctuating torque. Yeah, so there's actually a whole, I mean, buckling, I can really extend the amount of, but one needs to really have a two-part kind of session on buckling. Yeah, so I'm just reading a problem here, and I will definitely scan this in for you, but it's a connecting rod for slow vertical paraffin oil engine. And it basically incorporates the stuff you learned in heat engines, and you're basically applying it here. So I will scan this, I have it over here, and apply the same principles. Obviously, I've shown you that design. So that's what I'm saying. So if you have a column, one needs to be aware that anything in any column form, you must check for buckling, right? First, and then compression. Okay, so we just want to discuss the difference between the two. Obviously, we had a small conversation about it, very small. So basically, bending is a state of stress developed when a transverse load is applied, right? So it's applied perpendicular to the beam. Obviously, we're aware of this. We bend it, we get two states of stress, tension at the bottom, compression on the top. That is what bending is. It's not buckling. So the load is applied transversely or perpendicular, right? Is that the way we want to talk about it? With buckling is concerned, obviously, we have an axial load. It's applied along the direction of the so-called neutral axis, as they say, or the central axis. So that's what's important. It acts like a typical column. You've done several problems like this in the materials too. Remember a column and hollow column and all of this. And what you looked at initially was just the what's the word I'm looking for? The stresses. However, you never looked at buckling. You might find out that load, if you increase the load, the thing might buckle. Yes, so yeah. So when an object is unable to sustain the load, it suddenly collapses, and this collapse is called buckling. We talked about this. Buckling is a sudden change in the shape of the structural component and an axial load. So they're saying the structure is subjected to a gradual increase in axial load. When it reaches the critical level, which we work out, the structure will suddenly change shape, and the structure is so-called buckle. Right? Again, this does not, and will tend to happen. It depends on the material. For steel, in particular, it will happen before the yield. Right? So if a yield stress with respect to area gives you a stress of, let's say, it was 355, it can happen less than the allowable stress of 355. So I want you to be aware. So again, the actual loading can be both a normal axial load through the center of gravity or the neutral axis, or it could be an eccentric load. Remember the eccentric load we did? So as long as it's somewhat close to the axis, it can happen, or close to it's an actual type load. So eccentric load can induce the buckling phenomenon. Sorry about that. Again, this is just more examples between the two. I've got a few. Obviously, I'm just recapping, and obviously it's probably important. And that bending is a state of stress development. A transfer load is applied. We talked about it. Buckling is a state of instability. So I want to say that again. Buckling is a state of instability. It is not the same as a state of stress. It's not a state of stress. It's a state of instability. The experience, the deflection, deformation of a structural member like column leads to collapse of a structural member. Of course, it will collapse given that the load slowly increases. So can I ask you guys, in terms of stability, in terms of NAVOC, can you just hint to me who can let me think of how this ties in with NAVOC? I mean, I'm just thinking about it now. Yeah, so we basically here now. I'm just gonna really make highlight this. Okay, cool. squeeze it font here. It's a state of stability. That's what I really want to emphasize here. Okay, anyone? Is it a minus, Kessa?
Probably for your what's the name? Your transverse and longitudinal girders on the ship.
Okay.
Like in the floor design or the hull design. That makes sense, I think.
Yeah, no, I'm with you, but I mean, like in terms of NAVOC, you know, when you guys talk about stability, keeping the ship like stable.
Yeah.
Like relating, yeah. No, for sure. I know in the ship structure itself, obviously there's a lot of columns, right, which you have to check for that. But I mean, like, how does NAVOC relate to something called stability? I don't know. It's just a long shot question, really. There might not be any relationship, but I'm sure there is, because I remember buckling is of instability, not like, yeah, Jason.
So it would be then for the overloading of the ship.
Okay. You know, like very much to place of containers, otherwise it'll, you know, it will. I don't know if you guys like even with
sorry. To get a ship stable, you want to keep the weight as close as possible to the center of the ship. So are you saying that the load that's applied on the beam must be dead set in the middle?
Yeah, so we discussed that. It's not that it must be dead set in the middle. It depends on the section of the beam, and we'll talk about that here. But I'm just asking, maybe you guys are more specialists in NAVOC, maybe in the next year or so I might pick up on that. But I don't know if you've guys seen this. This has nothing to do with this, by the way. And I just thought I just have it over here. No, I'm getting that emails again. Yes, emails. Yeah, so are you guys aware of this fundamental error, sorry, which happened? But obviously this was the stability thing. I was discussing this with Mr. Prince. Obviously, again, this has nothing to do with what we. I just want to get I can send you this article. But I found this interesting, and obviously I think it's to do with it says there, when the chief officer made a fundamental error with the ballast quantity, obviously added too much, maybe too quick, but this is not anything. But anyway, and then obviously, but the idea is that I'm trying to say that it's a stability thing. What we're looking at, we're not looking at a typical strength of material thing. But anyway, I don't know if you guys are aware of the story about the Golden Day. This guy probably added too much water on the one side, and then
So if you want to find something really interesting on stability, you must look at parametric rolling.
Okay.
Parametric rolling for container ships, then you'll see exactly what stability is all about.
Okay, cool. Thanks. Yeah, so something similar to that. I'm trying to make you aware that what we're looking at here is not a particular a strengths, you know, like a strengths thing, blah blah blah. It's like when it's gonna break, and it's you're checking if this column is stable, right? This column stable. So there's two theories or two models or two theories, which hopefully one of you guys still wanna develop one day. We're gonna use the Euler. I think it's called Euler, not Euler. Maybe we can call it Euler. Yeah, that's a one theory which we predominantly use, and also the Rankine-Gordon light, which we'll be taking a look at. But Euler is the main one you're going to probably be focused on, definitely. But obviously both depending. But Euler, obviously, once you see it, makes sense. But be aware, this is the main ones. And okay, is it Alex? Okay, can you please mute your mic? And then just and obviously they're based on assumptions that the stat is perfectly straight and the loads applied actually. Now this is all not the case. Again, we're making this so that our models can work nicely. There are models which do account for the deviations with this within this formula. So we're just looking at the basics for now, in terms of the so-called volume. Just as an introduction or understand the concept of buckling. Yeah, all the do is since struts are not normally perfectly straight, these theories will give buckling loads that are far greater than the true buckling load of the strut. But since a factor of safety is used when designing a strut, the problem is not to see this. Yeah, that's a very important point. Can you use? No, you cannot. It's a different kind of thing. You can't use Macaulay's. It's a different kind of thing, right? I haven't done it myself. Maybe you can. Highly doubt it, right? So like I said, it's a stability check. This is not a strength of material check or yeah. So how the theory works, that's what Alex is basically talking about. There is a bit of Macaulay's in here. You can see the bending moment is d squared y over m. They do a subject, obviously for this particular load, it's m times py. Not talking too much in this. You end up with a second order differential equation in Maths 3. You have to solve this. And basically at the end of the day, you get this formula over here, right? Pi squared E I over L squared. I don't need to look at the equation for it. Pi squared E I over L squared. So what that formula means, guys, is that those three variables, right, is going to tell you whether something will buckle or not. Your elastic modulus, with the Kiefer, not with the load is, the elastic modulus, the second mode of area, and then L squared, right? And we'll talk about L squared, right? So let me just read that first text, and then that's the formula you're going to be using. Make sure you know this formula. I think it's in your formula sheet. So please be aware of it. So it says, so P critical, let me just read P critical. So after we've done a derivation and get to this formula, what P critical is, right? It is the critical maximum axial load on the column just before it begins to buckle, just before, right? So it means we add 1 million, arguably 1 million, it will take that shape as you see there, right? Just about to buckle. It says this load must not cause the stress in the column to exceed the proportional limit. So another thing what's important, and we'll discuss it later on, is that that load can't be higher than the what is this now? You know, your yield stress in essence, that particular, obviously then yielding will occur. So it's operating when it's in elastic state. This particular formula, which I'll discuss again, you'll see it's there, right? Elastic modulus, there you go. You can compare different structures. Obviously a bigger E will have a bigger buckling load. And let's go to I. Now I is very important. Very, very important. This is for you, I and L, or for you to figure out like within a test particularly. So let me explain to you what I mean by this. So it says it is important to realize a column or buckle about the principal axis of the cross-section have the least moment of inertia. So the weakest axis. So what I mean by that, if I can pull up a steel section table. So look at my textbook, a random one. I look at my table 2.1 I section IPA 100. I look at my IXX, I get 1.36, and my IYY, I get 0.126. In this case, it'll buckle across the y-axis, right? So it'll shift. If you look at the channel, the shift, it's what is this? What's what I'm looking for? The shift towards, it'll move left and right. So very important when you're doing analysis. You have to use the least moment of inertia, or the least second moment of area. That's for you to know. So I don't have to be saying this over and over. Obviously, that kind of makes sense. That's where it's going to buckle. Because remember, second moment of area, it's resistance to bending. So when it's going to be loaded up, it's going to find the quickest, the most easiest axis to bend. Sure, that's the one it's going to choose. Hope that makes sense. Figure 30.6, what they're showing there. It'll buckle about the AA axis and not the BB. Obviously, if you've done your typical BDQ over 12, that's giving you a demonstration that obviously your YY is a lot less than your BB, and it's going to buckle about AA there. And they say typically as a result, engineers try to keep the second amount of area the same on both axes. That's like the ending of what's happening. And then L is very important. And we can unpack L here. Obviously, so with the typical struts, they can be joined in different ways. And I'll probably use this one here. We could have both pin ends where on basically the strut is free to kind of rotate, arguably there. Not free to rotate, but you get the idea, there's some motion. We get fixed and free, fixed one end and free one end. I talk about that, and you get fixed ends as well, where they're both fixed. They really can't move. And where one is pin and one is fixed. Now you're seeing different K values there, right? So when we do it, obviously, that L squared over there will change depending on how you fix the beam. So for strut, for pin jointed, our equivalent is equal to the length. For one of the fixed and one of the free end is 2 times L. So we have to work at different equivalent lengths. So you kind of have to know the different equivalent lengths for different kind of struts. So a question will basically tell you, check for buckling for a strut with both ends fixed. So then you must know you have to take the equivalent length and divide it by 2. I am not sure, as it stands now, where the deriving comes from each one, but there is some form of logic in terms of the buckling. So one will buckle more, and we can do a small calculation to actually figure out, which one is given for, if anything else remains constant, which one is more weaker than the other one. Okay, so that's all. It's just some more examples to just show you the deflected shape, how it will look. Those are the 4 conditions you need to know. And then, yeah. So let's do our first warm-up example. I just came up with this one. I hope it's going to work out. Yeah. Any questions before I move on? Thank you, Alex.
So, once the beam or how do you say, the bar buckles, once you remove the load, does the beam return back to its original shape, or does it stay in that position?
So, like I said, if it's, it will go back to shape, right? That's why it must be in the proportional limit. Do you remember me? Do you recall me saying that, or was I like just rushing through?
Yeah.
It's possible. Yeah.
Okay.
If it exceeds that, obviously it will remain buckle. That text over there, P critical. Yeah.
Okay. Where was this? Okay. So that's obviously if that exceeds your E value, surely, because that's your
Yeah, not your E, it's more of your yield stress rather. Yeah, proportional to yield stress.
I thought I said that in the beginning. Okay, no way. Okay.
Well, yeah. Yeah, you talked about that. So anyway, so what we're gonna do now? This is an interesting example, right? I got inspiration from another YouTube video, which I watched, and I wanna check your understanding of buckling and yielding. We'll just quickly see. So I think let me just copy the whole example on the whiteboard. That'll be we basically getting towards the end here, so don't worry too much. You can just have to forgive me. I'm just gonna have to just get the whole thing. Okay, so I'd like you guys to just get your pens ready and stuff. Try to make this as fun as possible. Yeah. Okay. I should run some practicals when I was a test technician on this. Oh, here's a question. Oh no, that is one we addressed already. Always a bit of a headache getting this right. Okay. So what this goes for first is determine if it will yield, right? So that's simple. We go force over area. Obviously, we're assuming it's applied here. You get the idea. It's fixed, probably fixed on this end here, right? So if I do this, 20 by 50, say 200 kilonewtons, and I'm going to just divide by 0.02 times 0.05. All right. Yeah, we'll discuss that later. Let's just get this concept through. Yeah. So let's just have a look. So if I calculate that, what do I get? I get 200 megapascals, right? You guys get that? 200 MPa compressor. Our allowable is what? What is our allowable? 240? I think we're good. You agree with me? You guys happy with this? So we're under the level, right? Yeah, okay, thank you. I hope everyone gets that idea. So what it means when we check for this particular column, I should assume a column with a rectangular column, So anyway, now like I said, we have to check for buckling, right? So what I said now, we have to use E over I over L squared, right? So in this case, we're assuming pin, we're just going to use the actual length of this thing. So the length we're going to be using is 400 millimeters, 450, 500, and it obviously to 550 to 600, right? Okay, so first thing is first, we need to work out our I section. So can I get IXX from you guys and IYY and tell me which one you guys are gonna have to use? So I think I mean this when I say that, so even know that's 20 here and that's 50 here. Okay. I hope that looks right. Okay, let me just do it again. 20 by 50. Okay, so you guys can give me IXX and IYY, please. I'll give you guys a moment to calculate that.
Oh wait, hold on. So I get 208.33 times 10 to the minus 9 for IX.
Just give me a moment. So again,
208.33 times 10 to the minus 9.
208.33 times 10 meters to the power 4, right?
Yeah.
Okay, cool. I'm checking myself. Yeah, I'm happy with that. That's IXX, right?
Yes, sir.
IYY. You guys agree with these answers? Simple. Yeah.
33. Oh, there we are. Okay, you got it.
So, Mr. Kessel, which one do we use in our computations?
Wouldn't that be your IYY?
Beautiful. That's the idea. Yeah, there we go. Thank you. So, pi squared, 200 GPA, 33.33 times 10 to the negative 9. Divide that by L squared, right? So L is going to change. So we're going to go 0.4 first. And then we're gonna find the critical load for each of the stuff, right? So I'm just gonna have a small table here. Okay, let me just hope you guys get what I'm trying to do. Right, so the formula is there. And yeah,
it's basically like trying to sub in different values for x in your deflection to see where the maximum deflection is. Okay.
Something like it. Something I came up with. We're gonna discuss it, so don't worry. You'll see what I'm talking about. So should I maybe have, obviously everyone can see the values there, so we call it L, yeah, L and PE. Okay, cool. 0.4, 0.45, 0.5. So can I just get for each value here different what's gonna work out? Yeah. So just basically set the equation up and obviously just pi squared L squared.
Okay, P is it PE? It's PE.
Yeah, PE or PCR. Makes no
Okay, so
difference really. Yeah.
PE for a length of 400 mils is 411.2 kilonewtons.
Okay, next.
Then at 450 is 324.9 kilonewtons.
Okay, next.
Okay, at 500 mils, now it starts going down at 263.2 kilonewtons.
Cool.
And at 550, it's 217.5. So it's
Yeah.
217.5
Okay.
kilonewtons.
Let's keep going up. Or 665.
For 600 mils, 182.8 kilonewtons.
Yeah. Just go to 67. Yeah, 65, 67. I hope this is all right.
650 mils, 155.7 kilonewtons.
Yep. Last one.
And 700 mils, 134.3 kilonewtons.
I agree. Yeah. Because that is a small exercise, right? So, thanks for the cash. I appreciate that. So looking at all of this here, guys, right? At 400 moles, we get a P critical of 400. All right. What is this for? What do you think this value means? Let's engage you. Let me see, Mr. Matambo. Brent, yes.
That's the value that the beam will start, not the beam, the column will start buckling at.
Yes, exactly. So if we apply a 200 kilonewton, will it buckle?
Yes, it will buckle twice.
No.
No, it won't buckle. It's less than the maximum value. So.
Oh, sorry. It will. Yeah, sorry. No, it won't.
You know, right? Okay. Do we all get that concept? So we're applying 200 kilonewtons here, right? And if we have a 400 mole beam, a P critical will come to 411, right? So what it means is that if we apply a load of 415, for instance, this column will buckle. But in this case, we're only applying 200, so I can say no. Let's look at the next one.
So if you apply 200 at 600 mils, it will fail. It will buckle.
Say again.
If you apply a force of 200 kilonewtons at a beam of 600 mils, it will fail.
Yes,
buckle, yeah.
yes. You get it. Yeah. Does it make sense? Yes. Yes. Are you working with the Cassidy? You understand? But can you see what's interesting is that even though our allowable stretch is all right? You agree? So we're still in the right realm. But look, if we can make this column 600 more, this is gonna start to buckle. That's the concept, guys. Please tell me we didn't get that. I don't know if you're all with me. It's not a state of stress. It's a measure of stability, or a structural stability, if one could say that.
Okay.
I'm waiting for the bells to hit here. I don't know. It's not hitting everyone. Do we all get the concept, guys, or not? Thank you, Mr. Mantambo. Yeah, the max value. So you can see there, right? So 182.8. If you apply that 200 kilonewtons on here, that thing is gonna buckle. Even though it's not gonna fail by compression, it will buckle. So you must be careful how long you make your strut. And obviously, the longer it gets, the buckling load, the critical load will start to decrease. Very important. Alex, you want to say something? The mic is on.
Yeah, I just wanted to say something. I was trying to say, like, say for instance, you said, so I'm just going through my book here. Say for instance, you said that column that you have there was an I section, a parallel flange of 254 by 146 by 31. So then, your Ix will be 44.3 times 10 to the minus 6, and your y is 4.48. So you'd use your 4.48, your iy
Yeah.
in that
That is correct.
in that
Yeah.
equation.
That is correct. That is perfect.
Okay.
You
Okay.
really got me there. Yeah.
Okay.
That's
okay.
it. Yeah. That's it. Like if you do have a ruler here, you can check your even with the ruler and run a small experiment, and as you apply a load, a buckle or specific a buckle on the one side, and there's a reason why it's moving that way. So I really have no rule here. Anyway, yeah. But the concept, are you with the concept in that even though your column can withstand the stress, it will buckle. It can buckle. So hope everyone got that. Is anyone this question is just a concept question? That's basically all. So that you understand the concept of what buckling is. It's not like stress or whatever. In fact, what happens now, when you design this column, we're gonna have to use this load here. We know that okay, it'll buckle at depending on how long our column obviously is. We have to make adjustments here, so that we find a compromise between the area of the thing. Obviously, there's certain things which is fixed, which we can't really which we can't actually change and choose. But yeah, so one has to find a compromise between the two. So guys, if there's no questions, is everyone happy with this? Can we move on? We're basically getting there now. I mean, that is like for me, that is the main example. I just wanted to do that really. Lost, I'm not sure. Thank you. And then yeah, I do want to put up this picture here to show you like you do get different kinds of buckling. You can get a general local buckling. I'll discuss that now shortly. I can buckle and yes.
No, sorry. The what I said there is that basically the last question of test 2, you can basically do the exact same for this question, where
can you elaborate?
For where you said to find your maximum deflection, you would have to go and just play through your second moment area for different beams.
Yeah.
You can do the exact same thing. Yeah. That's to see which beam would buckle and which would.
Yes, exactly. Yeah, no, for sure. But nothing that critical, guys. It's towards the end, like I said, if I take this further, it'll really be in a very different place. Right. So okay, so the first example, we're gonna have one more. I don't know. Did I delete all the slides? Yeah, it seemed like I did. I was looking. These other things I want to mention. It's not even here. I was thinking, where the hell was it? But it was pertaining to you get different kinds of buckling. You can get torsional buckling and stuff like that. That's fine. It was really extra information. Okay, so let's just do one more. We don't want to spend too long on this. Just place that image there. So this one here, it's the example in the textbook. It's going to be quick, and the idea is to actually just get your pens out, quick play around, and here we're going to look at different conditions, right? Where it's both pin jointed, both fixed, one end, and then we have to calculate something small there. So I'll just copy that on the whiteboard again. Then yeah, we'll solve this. I'll take you where we need to be. Don't worry, we're getting there now. And the rest you can go figure out yourself. Not that difficult. But know your Euler theorem very well. You're gonna see me now. You're gonna see what I'm about very shortly. But let's just get used to this formula quickly. Please, guys, I really hope you can just just get used to it while we're here. Yeah, so we using the Euler formula. Remember, there is other formula, Rankine Gordon, another approach, making you aware, but this is the main one. And what we're just looking at here is a bar of some sort we apply an actual load and we are just basically having different conditions, right? So I recommend getting your textbook out and obviously just kind of checking the conditions because they'll all be there. Yeah. So in this case, they're talking about and it has a diameter. So first thing is first, let's write our formula down: PE or PU or P critical pi square EI over L square, and a typical LE because L is effective length and this changes up depending on the condition. So what's nice here, we're working with a bar. So right, so we obviously know that your I section is the same in both on the X and Y, so that's fortunate for us. So we can just use this, pi over 64 times that. Nice example. So pi over 64, 20 times 10 to the negative 3, and you get 19.6 5, right? Just check it on. So you guys happy with it?
Okay, 7.854 times 10 to the minus 9.
Oh, my bad. Yeah, thank you. Can you see? Here we go. 7 point. Yeah, I squared instead. You can literally see me right squared there. Cool. All right, so that's 7,854. So again, this is the concept of what buckling is, and you understood, right? There can be a compressive load and all of that. So all we're doing here, we are just simply changing the effective length. We're just changing LE. So what I want you to do now is for the first condition for A, they're both pin jointed, and what that really means, again, they're free to move, and for your equivalent length in this case will be equal to L. All right. For your next condition, they're both fixed. Make sure you know this. That's 2L. Right. Make sure you know this. The mark just comes from really knowing. Right. Obviously, you're gonna have to think about it. So that is going to be for one fixed, the other pinned, I think, and the last one will just be what's the other one? One fixed and the other one free, which will be LE equals 2 times L. So in this case, we have 1 meter. So all we're going to do is, I'll just write it like this here, pi squared. We've got our elastic modulus. Luckily, it's on both axes the same. Always remember, use least second moment. In this case, we're fortunate. As part of the understanding of where it buckles, that's 7,854. Fortunately, it's the same. The shape is symmetrical, and like I said over here, L is going to change depending. So in the first case, L is going to be 1 squared, and let's get that answer here. So let's get PE here, PE here, PE here, PE here.
So I don't understand where they're getting this 4, 2, and 0.5 from. 0.25.
Excuse me?
Okay, no one. So your PE there for your big equation is 15.5.
15.5. PE.
Yeah, for this pi squared times 200 times 700.
Yeah, okay, so 15.5, right?
Yes.
This one. That's what that's just using 1 square, right?
Yes.
Yeah. Okay, that's good. Next condition, let's see.
Yeah, so I don't understand why they're doing 4 times them by 4.
It's simple, man. It's you're talking about oh, I made a mistake here. Let me just quickly see what is the second condition? Second condition is both fixed ends, and that's both fixed ends will be L over 2, sorry. Yeah. I'll explain to you now. L over 2, right? Like that?
Yeah.
The reason why it's 4 is because if you have that square, it's 1 over 4, and just They're basically doing a flip in times. I hope you get that.
Say again. I didn't hear you again. Say they basically
Okay,
what?
so it's half. It's 1 times a half, right? Which is a half, right?
Yeah.
And then you move that, and then you're left with a quarter, right?
Yeah.
Flip in
Yeah.
times.
Okay. Okay. All right.
Yeah.
All right. All right. I get
That's
you.
all. So times by 4, you know, that kind of thing.
Okay.
Okay, so PE, the
So
next
for-
one,
For both
you can
ends
just plug in like
fixed.
a half and whatever. Yeah.
So both ends fixed will be
Yeah,
4 times 15.5.
yeah, which will be 16.2.
62.012.
Yeah. Okay. So again, we can already see, depending on the condition, is that for when it's fixed, there is a higher critical load. So this is the idea, which is kind of being well, for this particular section, obviously, but it'll follow suit similar. That's what they're kind of trying to show. So if we look at the next one, which will be that's one fixed and the other pinned. Just get all of this. Just get used to the equation. 1 over root 2 squared. Yeah, I get 30.99. And then the last one is 2 times the length, right? Which is just 2. That'll be 3,876. So we look at what we could say is that the most stable is obviously the most stable thing, right? It depends on obviously the load we're going to induce, but if we were to apply an actual load, your both ends fixed, which kind of makes sense, is most stable. Is the most stable. And the least stable is obviously the last one, and that is obviously the one with one end fixed and the other end free. So can you see? So obviously it's more fixed. If it's fixed here, it's harder to buckle. But if you have one obviously open, one free, so yeah, that is quite interesting. So I want you to be aware of at least the max and the min there. So obviously the way you design your strut, you also need to be aware of what do we call this? We need to be aware of how we so what are they saying there? So for the case of A, and obviously so we just heading on to E now. So for the case of A, they also wanting to calculate the maximum deflection before the yield strength is reached, right? So what they're saying is that they wanting to use the P critical of A, right? Of A and divided by the area. So we do that. Guys, are you still there? Are you still following? Are you tired of the test?
I'm still here, so.
Yeah, okay, thanks. I was like I'm talking to myself here. Yeah. Get in there, guys. We're nearly there, man. Don't stress too much. Thank you, Mr. Matoso. Thanks, Skifa. And what they say is that before the yield is actually reached, right? So what they basically do is just take the yield. So they take the maximum load and they subtract. So what this means is that if you apply that load, you only get a 49.348 megapascals induced. Obviously, that's small for us. The fact that we know that is steel, right? But they're saying that what's the word they said there? Before the yield, right? So you subtract the value from the so-called max value of what it is, and you get an answer of 250.65. Obviously, this is just because before the yields. Because we can't be on the 300 because then obviously it's going to yield. So this is like just before the yield. So just something you kind of have to remember if you ever see it again. And we basically use this formula over here because they want the maximum deflection, right? And I'll talk to that now. And what we need to do is find the moment. On the moment, it's going to be P times, I'm going to call it, can just call it X. And what I mean by X is this distance. Because remember, they use the same concept from deflection of beams, which I think Alex was kind of talking to. And obviously it's called Y, you'll see it now, but what they're asking for is, remember, at the end of the day, that this load is producing a moment P times Y, right? In this case, I should actually just call it Y here, but you get the idea. So what they're asking for is this distance, right? Just be aware, right? Again, just before it's yeah. Then what happens now? We take them. We're looking for M. We've got the stress now before the yields, arguably before the yields here. The I section we have as well. That's 7,854 times 10 to the negative 9, and you're dividing it by Y, which is 0.01. Obviously, that's your maximum neutral axis, and you'll find that you get a bending moment of. So this moment here, from that P times that, is basically a moment of 196.96. And in the end, obviously, all we have to do is just that load was that is P critical, if you remember, of A, and that is 15.5. So moment equals P times, can we call it the Y, PE times Y. That's 196.86 times 15.5 times times Y, and all you have to basically do is divide it through. So you can actually roughly find how much that, what was lateral deflection basically. This is the real purpose of the thing. That's on kilonewtons, and then so what I get here is 12.7 millimeters. Right. Just before the yields, right? So it's not going to remain like this. So if you remove this load with the Casa, it will go back to its normal shape. It's like if you take a ruler and you actually bend it. Remember, 12 mils not that much for if you look at the steel, depending on how long it is, like a meter. 10 mils, it's arguably, you know, small. Okay, are you guys all good now? Where are we now? Let me have a look. Any questions, guys? Understand the concept of buckling? Okay, guys, so what we're going to do now, I don't know if you guys want a small break, just like a 5-10 minute break. And please, the next part is of critical importance. I expect you to be full force on this one, because this is going to explain, it's actually just going to explain, no, it's going to take us to where we need to be. So let's just have a 10-minute break. Let's come back at 25 minutes past. But please, the next part, I want you to be interactive. We need to. This is what I'm. You understand? Once I start talking to it, like, oh, this is what he's going to do in the test or the exam. So that is why I want you to really get engaged in the next part. Okay, guys, see you at 25 minutes past. We'll call it end of part 1 here, and part 2 will be Won't be long. I'll just talk to the Rankine Gordon formula, and yeah, you guys can just I'll just end the lecture there. Okay. See you at that time. We should be done by 4 o'clock.